Imagine standing at the edge of existence itself, where the laws of physics twist into impossible knots, where time runs backward, and where the universe vomits instead of swallows. Picture a cosmic fountain spewing out matter, energy, and light with such violence that nothing, not even the fastest particles in creation, can approach it. This is not science fiction. This is not fantasy. This is the theoretical reality of white holes, one of the most bizarre, mind-bending predictions that mathematics has ever forced us to consider. And here's what should terrify and fascinate you in equal measure. They might be real, they might explain where we came from, and if you could somehow witness one, you would be watching the universe break every rule you thought it followed. Close your eyes for a moment and think about a black hole. You've heard of them, you've seen the simulations. Perhaps you've even gazed at that famous orange ring photograph that captured the world's imagination. Black holes are cosmic predators, gravitational monsters so powerful that they devour everything within reach. Light, matter, time itself. All of it gets dragged past a point of no return called the event horizon, disappearing forever into a singularity we cannot understand. They are the universe's ultimate prisons, one-way streets into oblivion. Now, flip that image completely. Reverse it. Imagine instead a cosmic geyser, a point in space from which everything erupts outward, where nothing can enter, where the universe screams matter and energy into existence with unstoppable fury. That is a white hole. The mathematical mirror image of black holes, equally predicted by Einstein's equations, equally consistent with general relativity, yet utterly, impossibly strange. But here's the question that should be burning in your mind right now. If black holes and white holes are equally valid solutions to the same equations, if the mathematics treats them as two sides of the same cosmic coin, then why have we photographed black holes, detected their gravitational waves, and observed their effects across the universe? While white holes remain phantom entities that exist only in theoretical papers and late-night conversations between physicists. What makes black holes real and white holes impossible? Or are they impossible at all? Let's go back to the beginning, to the moment when white holes first emerged from the abstract realm of pure mathematics. The year was 1915, just weeks after Albert Einstein published his general theory of relativity, forever changing how humanity understood gravity, space, and time. A German physicist named Karl Schwarzschild, serving on the Russian front during the First World War, somehow found time between artillery barrages and the chaos of combat to solve Einstein's notoriously complicated field equations. Imagine that scene for a moment. Trenches filled with mud and death, the constant thunder of guns, and there, by candlelight in a military tent, a man scribbling equations that would unlock the secrets of the universe's most extreme objects. Schwarzschild found an exact solution that described what we now call a black hole, though that term wouldn't be coined for another 50 years. But hidden within his solution, like a ghost in the machine, was something else. The mathematics contained a mirror structure, a white hole, ejecting everything while its dark twin consumed all. Schwarzschild himself wouldn't live to explore this discovery. He died just months later from a disease contracted at the front, his brilliant mind extinguished at age 42. But his equations survived, and within them lay a symmetry that physicists couldn't ignore. If you take the Schwarzschild solution and reverse the direction of time, you get a white hole. It's that simple and that complicated. Time reversal is a valid operation in physics. Most physical laws don't care which direction time flows. They work just as well backward as forward. An electron moving forward through time looks exactly like a positron moving backward through time. A film of billiard balls colliding runs perfectly fine in reverse, at least for a few seconds before entropy and friction become obvious. So why shouldn't gravity have a time-reversed version? Why shouldn't there be regions where space-time curves in the opposite way, creating cosmic fountains instead of cosmic drains? For decades, white holes were mathematical curiosities, footnotes in textbooks, exotic solutions that physicists acknowledged but didn't take seriously. After all, the universe seemed full of black holes, or at least full of objects that collapsed toward becoming black holes. Massive stars died, their cores imploding, creating the conditions for event horizons to form. We had a mechanism, a process, a narrative that explained how black holes came to exist. But white holes, how would you create one? You can't compress matter until it explodes outward forever. You can't build a fountain that violates thermodynamics. The second law of thermodynamics, that inexorable march toward disorder and entropy, seems to forbid white holes from existing in our universe. A white hole would be an island of decreasing entropy in a universe where entropy always increases. It would be like watching a shattered glass spontaneously reassemble itself, like seeing smoke flow back into a candle, like witnessing a cosmic impossibility. Yet the mathematics doesn't care about our intuitions. The equations don't know what seems reasonable to human minds. They simply describe what spacetime can do when bent by gravity, and they insist that white holes are possible. This tension between mathematical validity and physical plausibility has haunted physics for over a century. Some of the greatest minds in science have wrestled with it. Stephen Hawking, whose work on black hole thermodynamics revolutionized our understanding of these objects, explored white holes and found them deeply problematic. He showed that black holes emit radiation, now called Hawking radiation, because of quantum effects near the event horizon. This means black holes aren't entirely black. They glow faintly and, over unimaginable timescales, they evaporate. But white holes? The same analysis suggests they would be unstable, that any attempt to create one would immediately collapse into a black hole. The universe, it seems, prefers to swallow rather than spit. But let me ask you something. Have you ever considered that you might be inside a white hole right now? That the room you're in, the planet beneath your feet, the stars above your head, all of it might be the interior of a white hole that erupted into existence 13.8 billion years ago? Because there's a theory, a genuine scientific hypothesis proposed by serious physicists, that the Big Bang itself was a white hole. Think about what we know about the beginning of the universe. All of space, all of matter, all of energy, compressed into an infinitesimally small point, then suddenly, explosively, expanding outward in all directions. Everything racing away from everything else, the universe growing, inflating, matter and energy spreading through space. Doesn't that sound familiar? Doesn't that sound like matter and energy being ejected from a single point, unable to fall back in, pushed outward by the very structure of space-time itself? This isn't just poetic metaphor. In 2014, physicists Hal Haggard and Carlo Rovelli published a paper suggesting that black holes might not lead to singularities at all. Instead, they proposed that quantum effects at the heart of a black hole could cause it to rebound, transforming it into a white hole. According to their calculations, matter falling into a black hole would be compressed to extreme densities, but before reaching infinite density, quantum gravity effects would create a bounce, a reversal, turning the black hole into a white hole that ejects everything back out. For an outside observer, this process would take longer than the current age of the universe because of time dilation, but for the matter falling in, the transition could happen relatively quickly. Even more mind-bending, they suggested that our Big Bang might have been exactly this kind of rebound, the white hole phase of a black hole that formed in a previous universe. Let your mind sit with that idea for a moment. Imagine that our entire universe, everything we see and measure, all the galaxies, all the stars, all the atoms in your body, came spewing out of a black hole from another reality. That black hole, in some parent universe we can never observe, swallowed matter and energy until quantum effects caused it to bounce, to reverse, to become a white hole, and we are living inside the explosion of that reversal. Time itself began at that moment for us, so we can't see or measure what came before, but mathematically, structurally, there could have been something before. This theory elegantly solves several puzzles. It explains why the Big Bang looks like a white hole, why the universe is expanding, why we seem to be inside an event horizon in reverse. But it also raises profoundly unsettling questions. If our universe is a white hole from another universe's black hole, what happens to the black holes in our universe? Do they bounce too? Do they create baby universes, pocket realities that branch off from our own, forever beyond our reach? Consider the geometry of these objects. A black hole's event horizon is a one-way membrane, but the one-way direction is inward. Cross that boundary and you can never return. All possible paths through space-time, every trajectory you could follow, every way you could fire your rockets, leads deeper toward the singularity. Outside the event horizon, you can escape if you move fast enough. Inside, escape isn't just difficult, it's geometrically impossible, written into the structure of space-time itself. Now imagine the reverse. A white hole has an event horizon too, but it's one way in the opposite direction. Outside, you can exist normally. But try to approach it, try to cross that boundary inward, and you find that all paths lead away. The geometry of space-time itself pushes you out. You could fire your engines at maximum thrust, you could fall toward it with the speed of light, and somehow, impossibly, you would find yourself being repelled. Not by a force, not by pressure or energy, but by the shape of reality itself. How would that look? How would it feel? Imagine you're in a spacecraft approaching a white hole. From a distance, it might look somewhat like a black hole, a region of warped spacetime, perhaps surrounded by glowing matter. But as you get closer, you notice something wrong. The light isn't spiraling inward. It's bursting outward. Particles and radiation aren't falling into the horizon. They're erupting from it in all directions, and they're moving fast, propelled by the curvature of space. You fire your engines, pushing toward the horizon, but your instruments show you're not getting closer. In fact, you're drifting away, and the harder you thrust forward, the faster you seem to move backward. It's as if space itself is expanding between you and the horizon, as if the universe is determined to keep you at a distance. You'd be witnessing geometry as an obstacle, the shape of the cosmos refusing your passage. Some physicists have pointed out that this repulsive nature might make white holes invisible to us. If light and matter can't approach the horizon from outside, then we could never send a probe to investigate. We could never touch it, sample it, or study it up close. More troublingly, if the white hole is ejecting matter and radiation, that material would carry no information about what's inside. In fact, there might not be an inside in any meaningful sense. A white hole might be less like an object and more like a boundary, an edge of space-time beyond which there is nothing, or beyond which lies a region we can never access or observe. This raises a philosophical question as much as a physical one. Can something be real if it's impossible to interact with? If white holes exist but we can never touch them, never study them, never confirm their properties, are they part of our universe at all? Yet here's where the story takes a fascinating turn. In recent years, astronomers have observed phenomena that don't quite fit our models. Cosmic events that make some researchers wonder if we might be seeing white holes without recognizing them. Gamma ray bursts, the most energetic explosions in the universe besides the Big Bang itself, release more energy in a few seconds than our sun will produce in its entire lifetime. We think most of them come from supernovae or colliding neutron stars, but some gamma ray bursts don't match the patterns we expect. They're too bright, too brief, or too strange in their energy signatures. Could some of them be white holes? Could we be witnessing matter and energy erupting from these theoretical fountains, mistaking them for other phenomena because we don't know what a white hole is supposed to look like? In 2006, a team of physicists proposed that fast radio bursts, mysterious pulses of radio waves that last only milliseconds but release enormous amounts of energy, might be signals from white holes. These bursts have puzzled astronomers since their discovery. They come from distant galaxies, they don't repeat in predictable patterns, though some do repeat, and we don't have a definitive explanation for what causes them. Most researchers favor explanations involving magnetars, incredibly magnetic neutron stars, but the white hole hypothesis hasn't been ruled out. If a white hole existed, if it was ejecting matter in our direction, the radiation from that ejection might produce exactly the kind of brief, intense radio pulse we observe. It's speculative, it's far from proven, but it's not impossible. Think about what it would mean if we discovered a white hole tomorrow. Imagine the headlines, the scientific revolution, the complete upheaval of our understanding. We'd have proof that time-reverse solutions to Einstein's equations aren't just mathematical games. We'd have evidence that the universe is stranger, more varied, more baroque in its structures than we imagined. We'd have to reconsider everything we think we know about black holes, about cosmology, about the nature of time itself. Because if white holes exist, then time symmetry in gravity is real. The universe doesn't just allow objects that pull, it allows objects that push. And if that's true, what else have we been wrong about? But let's explore the darker implications, the reasons why many physicists hope white holes don't exist. Thermodynamics, the science of heat and energy, is built on the principle that entropy always increases. Disorder grows. Heat flows from hot to cold, never the reverse, without work being done. Eggs break, they don't unbreak. This isn't just a tendency. It's a fundamental law that governs everything from car engines to the death of stars to the ultimate fate of the universe. Black holes fit neatly into thermodynamics. They have entropy, proportional to the area of their event horizon. They increase the total entropy of the universe by swallowing matter and information. They follow the rules, or at least they seem to after Hawking showed they have temperature and can radiate. White holes, though, they're thermodynamic nightmares. If a white hole ejects matter and energy, it's locally decreasing entropy, creating order from disorder, violating the second law in the most flagrant way possible. You could, in theory, use a white hole to build a perpetual motion machine, to extract unlimited energy, to reverse aging and decay. The fact that we don't see these violations everywhere, that the universe stubbornly obeys thermodynamics at every scale we can measure, suggests strongly that white holes either don't exist or can't exist for long. Perhaps they're unstable, flickering into existence for fractions of a second before collapsing. Perhaps they existed only in the early universe when conditions were so extreme that normal rules didn't apply. Or perhaps the mathematics is lying to us, and white holes are pure fantasy despite what the equations say. Stephen Hawking addressed this in his later work. He suggested that white holes are theoretically possible but practically impossible, that any attempt to create one would require such precise, fine-tuned conditions that the slightest perturbation would destroy it. Imagine trying to balance a pencil on its point, but the pencil is made of space-time, and the slightest quantum fluctuation, the faintest gravitational wave, the most distant particle interaction, would knock it over. White holes might be infinitely fragile, existing only in the idealized vacuum of mathematical theory, unable to survive in the messy, chaotic, quantum jittering reality we inhabit. Yet there's another possibility, one that's even more speculative but utterly captivating. What if white holes exist, but not in our space? What if they're the other end of wormholes, Einstein-Rosen bridges connecting distant points in the universe or even connecting different universes entirely? According to some solutions of Einstein's equations, every black hole is connected to a white hole through a tunnel in spacetime. Fall into a black hole, travel through the wormhole, and you emerge from a white hole somewhere else. It's the ultimate cosmic shortcut, a wormhole connecting two event horizons. The black hole pulls you in, the white hole spits you out. Before you get too excited about using this for interstellar travel, let me crush your hopes with reality. These wormholes, even if they exist, are catastrophically unstable. They collapse almost instantly, faster than light could cross them, let alone a spaceship. You'd need exotic matter, matter with negative energy density, to hold them open, and we've never observed such matter in quantities larger than minuscule quantum fluctuations. Even if you could stabilize a wormhole, the tidal forces near the event horizons would rip apart any normal matter. You'd be spaghettified, stretched by differential gravity until your atoms separated. And even if you survived that, general relativity forbids certain kinds of time travel and faster-than-light travel through these structures. The universe has safeguards, built-in protections against paradoxes and violations. But still, the theoretical possibility remains. Somewhere, perhaps A black hole connects to a white hole, and matter flows eternally from one to the other, trapped in a cosmic cycle we can barely imagine. Let's talk about what would happen if you could somehow observe a white hole up close, if you could park your spacecraft at a safe distance and watch.
What would you see?
This is where we enter pure speculation, since no one has ever seen one, but we can use physics to make educated guesses. First, you'd notice the light. A white hole would be bright, potentially blindingly so, because it's ejecting photons as well as matter. The event horizon would glow with radiation, perhaps across the entire electromagnetic spectrum, from radio waves to gamma rays. The intensity would depend on how much matter the white hole is ejecting and how fast. If it's spewing out stellar masses, you'd see something brighter than a supernova, a sustained explosion that never ends. Around the white hole, you might see a shell of matter, material that's been ejected and is now flying outward at enormous speeds. This shell would be hot, compressed by its own gravity and by the collision of particles moving at different velocities. It might shine with X-rays, it might generate shock waves, it might even trigger fusion reactions as hydrogen nuclei slam together with enough force to merge into helium. The region around a white hole could look like a stellar nursery in reverse, a place where matter is being born rather than condensed, where the raw ingredients of stars and planets burst into space already energized, already moving. But here's something that will twist your mind even further. Time dilation. Just as time slows down near a black hole's event horizon, it would behave strangely near a white hole. An observer far away would see time near the white hole running differently, though the details depend on the exact geometry. Some calculations suggest that time would appear to run backward near a white hole, at least from certain perspectives. Imagine watching particles emerge from the horizon. From your distant viewpoint, they might seem to move in reverse, their trajectories tracing backward through time before suddenly flipping forward once they're far enough from the horizon. You'd be watching causality break, effects preceding causes, the future determining the past. It would be nauseating, disorienting, a visual representation of how thoroughly white holes violate our intuitions about time. Now ask yourself, if white holes are real, could we use them for anything? Could they be sources of energy, fountains of matter, gateways to other places or times? The answer, frustratingly, is probably no. Even if white holes exist, their repulsive nature means we can't approach them to build collectors or harness their output. The matter they eject would be moving too fast to capture easily, scattered across vast volumes of space. And if they're unstable or short-lived, they'd be useless for any practical application. But imagine for a moment that we found a stable white hole, one that had been ejecting matter for billions of years. The region around it would be dense with material, a vast cloud of gas and dust, all carrying the kinetic energy of ejection. Could civilizations harvest that cloud? Could they build Dyson swarms around white holes instead of stars, capturing matter and energy as it erupts? It's fun to speculate, but we're so far from having the evidence or the technology that it's pure science fiction. There's a related concept that some physicists have explored: white fountains. These would be weaker versions of white holes, regions where matter is ejected but not with the full intensity and geometric impossibility of a true white hole. A white fountain might be observable, might be something we could detect with telescopes, and might occur naturally in certain cosmological scenarios. Some researchers have suggested that the cores of quasars, those incredibly luminous objects powered by supermassive black holes in the early universe, might have white fountain components. The jets that shoot from quasar cores, beams of matter and energy that stretch for thousands of light years, might be driven not just by the black hole's accretion disk, but by white fountain effects at the very center. This is highly speculative, but it's an attempt to connect theory with observation, to find a place in the real universe for these mathematical phantoms. Let me take you back to the fundamental question. Why do black holes exist but white holes apparently don't? One answer involves the arrow of time. We experience time as flowing in one direction, from past to future. We remember yesterday, not tomorrow. We see causes followed by effects, never the reverse. This arrow of time is tied to entropy, to the second law of thermodynamics. The universe started in a low entropy state at the Big Bang and has been increasing in entropy ever since. Everything that happens, every process, every interaction, pushes the total entropy higher. Black holes fit this narrative. Their endpoints, final states, maximum entropy configurations for a given mass. Matter collapses, entropy increases, and you get a black hole. It's thermodynamically favorable. White holes run against the arrow. They would decrease local entropy. They would represent matter uncollapsing, processes running in reverse. In a universe with a strong thermodynamic arrow pointing from past to future, white holes are anachronisms, objects that belong to a time-reversed universe. Perhaps they could have existed in the very early universe, in the first fractions of a second after the Big Bang, when conditions were so extreme and so far from equilibrium that the arrow of time hadn't been established yet. In that primordial chaos, white holes and black holes might have been equally common, both forming from quantum fluctuations in the seething space-time foam. But as the universe expanded and cooled, as entropy increased and the arrow of time became dominant, white holes would have become unstable, collapsing or evaporating, leaving only black holes behind. This brings us to one of the most beautiful and strange ideas in modern cosmology. The possibility that white holes are related to the Big Bang not just metaphorically but literally. When we trace the expansion of the universe backward in time, we see everything converging on a single point, the initial singularity. But singularities are places where our physics breaks down, where general relativity gives nonsensical answers like infinite density and infinite curvature. We don't really believe the universe came from a mathematical singularity. We think quantum effects, perhaps described by a theory of quantum gravity we haven't fully developed yet, smooth out the singularity into something else. What if that something else is a white hole horizon? Picture this scenario. Before the Big Bang, there was a collapsing region in some larger space-time, a black hole forming. Matter and energy fell inward, compressed by gravity, approaching what would have been a singularity. But quantum gravity effects intervened. The collapse halted, reversed, bounced. The black hole became a white hole, and everything that had fallen in came erupting back out, but not into the same space-time it came from. The white hole opened into a new region, a new space-time, which we experience as our universe. The Big Bang was the moment we crossed the white hole's event horizon, the moment we emerged into this expanding cosmos. And if that's true, then we're not in a normal universe at all. We're inside a white hole that's been erupting for 13.8 billion years, and the expansion we observe, the Hubble flow that carries galaxies away from each other, is just the ongoing ejection of matter in space from that primordial white hole event. Does that idea excite you? Does it terrify you? Both reactions are appropriate. If true, it would mean the universe has an inside and an outside, that there's a boundary to reality we can never cross or see because it's in our past, hidden behind the cosmological horizon. It would mean that asking what happened before the Big Bang is like asking what's on the other side of a white hole horizon. Geometrically forbidden, observationally inaccessible, but potentially real nonetheless. And it would mean that our universe might not be unique. Every black hole in our cosmos could be doing the same thing, creating white hole universes that branch off from ours, babies born from collapsing stars, each with its own laws, its own constants, its own history playing out beyond our sight. Let's examine the observational challenges. How would we detect a white hole if one existed? This is where the theoretical rubber meets the observational road, and it's not a smooth ride. A white hole would be ejecting matter and radiation, so it should be bright, but so are many other astrophysical objects. Supernovae explode, quasars blaze, gamma ray bursts flash. How do you tell a white hole from these other phenomena? You'd need a signature, a unique characteristic that only a white hole would have. Some researchers have proposed looking for objects that emit radiation but have no visible source, regions of space where energy appears to be coming from nowhere. Others suggest looking for violations of causality, events where the light curve or energy spectrum doesn't make sense in forward time, but would make sense if time were running backward. In 2021, a team of astrophysicists analyzed a peculiar gamma-ray burst detected in 2006, catalogued as GRB 060614. This burst was unusual because it lasted longer than most short gamma-ray bursts but didn't have the supernova signature associated with long bursts. The researchers modeled what a white hole ejection event might look like and found that it matched the observed properties remarkably well. They were careful to note that this wasn't proof, just a possibility, and that other explanations might also fit the data. But it was tantalizing. Here was a real astronomical event that could, conceivably, be a white hole. Telescopes are scanning it, analyzing it, looking for follow-up signals. So far, nothing conclusive. But the possibility remains. Think about the implications of confirmation. Imagine the headline, "White hole discovered in distant galaxy." The scientific community would erupt. Physicists would scramble to revise models. Astronomers would point every telescope at the object. Theorists would publish hundreds of papers exploring what it means. The discovery would be comparable to the first detection of gravitational waves or the first image of a black hole, a milestone in our understanding of the universe. It would also raise immediate questions. Is it unique, or are there more? How did it form? How long will it last? Can we study it over time? And most intriguingly, what is it ejecting? Is it matter from our universe, or is it spewing out material from somewhere else, from another cosmos, giving us a window into a reality beyond our own? But let's balance speculation with skepticism. Many, perhaps most, physicists believe white holes don't exist and can't exist in any practical sense. The arguments are compelling. White holes require such specific initial conditions that they're essentially impossible to create after the Big Bang. They violate thermodynamics in ways that should make them unstable. We've never observed anything that unambiguously requires a white hole explanation. And some of the theoretical models that predict white holes also predict other unobserved phenomena, which makes those models suspect. The principle of Occam's razor suggests we shouldn't multiply entities unnecessarily. If black holes alone explain our observations, why invoke white holes? Yet science has a history of confirming the seemingly impossible. Black holes themselves were once considered too bizarre to be real. When Schwarzschild first derived his solution, many scientists, including Einstein, doubted that nature would actually produce such extreme objects. They seemed like mathematical artifacts, curiosities that arose from taking the equations too seriously. It wasn't until the 1960s, with the discovery of quasars and X-ray sources like Cygnus X1, that the scientific community accepted black holes as real. Today, we've imaged them, we've detected their gravitational waves, we've measured their properties with exquisite precision. What seemed impossible became undeniable. Could white holes follow the same path? There's also the question of what happens to information that falls into a black hole. This is one of the deepest puzzles in theoretical physics, the black hole information paradox. Quantum mechanics says information cannot be destroyed, yet black holes seem to destroy information by swallowing it and eventually evaporating via Hawking radiation, which carries no information about what fell in. This paradox has tormented physicists for decades. Some propose that information is encoded on the event horizon, stored in a holographic way. Others suggest it's released slowly through the Hawking radiation, though calculations show this seems impossible. And a few radical thinkers propose that the information isn't destroyed or preserved, it's transferred somewhere else. To a white hole, perhaps on the other side of a wormhole or in another universe. The matter that falls into a black hole would emerge from a white hole, carrying its information with it, preserving quantum mechanics at the cost of losing that information from our observable universe. If this is true, then white holes aren't just theoretical curiosities. They're essential components of cosmic information processing, the universe's way of preserving its quantum integrity. Every black hole would need a corresponding white hole, somewhere and somewhen, to ensure information isn't lost. This wouldn't necessarily make white holes observable from our location in spacetime, but it would make them fundamentally necessary for the consistency of physics. The universe would be far more connected, far more baroque than we imagine, with hidden channels and flows of information threading through the fabric of reality. Now let me ask you to consider something deeply personal. Does the existence or non-existence of white holes matter to you? Should it matter? On one level, they're abstract, distant, irrelevant to your daily life. Whether white holes are real or imaginary won't change your commute, your relationships, your immediate concerns. But on another level, these questions strike at the heart of what it means to understand reality. We live in a universe governed by mathematical laws, and those laws predict things we haven't seen. How we respond to those predictions, how we test them, how we refine our theories when they fail or succeed, defines our relationship with the cosmos. We are, as far as we know, the only beings capable of asking these questions, of doing the science, of peering into the equations and wondering what they mean. That's not trivial. That's profound. The story of white holes is also a story about the limits of knowledge. There are things we can calculate that we cannot observe, predictions we can make that we cannot test, at least not yet, and maybe not ever. This is humbling. It reminds us that the universe doesn't owe us answers, that reality is under no obligation to be comprehensible or accessible. We've come stunningly far in 4 centuries of modern science, from Galileo's telescope to the Large Hadron Collider, from Newton's laws to quantum field theory. But we're still fumbling in the dark, still guessing, still building models that are surely wrong in details and maybe wrong in essentials. White holes sit at that frontier, that edge where mathematics and reality may or may not align, and exploring that edge is how we learn. Consider the technological implications, speculative though they are. If white holes exist, and if we could somehow interact with them, they might provide resources or capabilities beyond anything we can currently imagine. A white hole ejecting matter could be a source of raw material, atoms and energy flowing endlessly from space-time itself. If the matter is ordinary baryonic matter, hydrogen and helium and heavier elements, it could be harvested to build structures, fuel stars, or support civilizations. If the white hole is connected to a black hole via a wormhole, it might offer a way to dispose of waste, to send refuse and entropy somewhere else, cleaning our local environment at the expense of some distant region. These are fantasies, extrapolations built on foundations of sand, but they're the kinds of fantasies that motivate exploration and discovery. On the other hand, white holes could be dangerous. An object that violently ejects matter and radiation, that warps spacetime in extreme ways, that might be unstable or unpredictable, is not something you want near your home star. If a white hole were to appear in our solar system, the consequences could be catastrophic. The ejected matter could collide with planets. The radiation could sterilize biospheres. The gravitational disruption could fling worlds out of their orbits. This is the dual nature of extreme physics. It offers wonders and terrors in equal measure. The same principles that allow for white holes as fountains of creation also allow for them as engines of destruction. Understanding them, even theoretically, is an exercise in respecting the power and indifference of the cosmos. Let's explore one more avenue, the connection between white holes and the multiverse. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that every quantum event branches reality into multiple universes, each representing a different outcome. This creates an unimaginably vast multiverse, a landscape of diverging timelines and possibilities. If white holes are real, and if they can connect different regions of spacetime or even different universes, they might be the bridges between branches of the multiverse. A black hole in one universe might become a white hole in another, linking them causally even though they're otherwise separate. Information and matter could flow from one branch to another, creating correlations, coincidences, or influences that seem inexplicable within a single universe. This is, to be clear, wild speculation layered on top of controversial interpretations of unproven theories. But it's the kind of speculation that stretches the mind, that forces you to think about the nature of existence in radically new ways. If the multiverse is real and if white holes bridge it, then asking, where does the matter from a white hole come from, has an answer. It comes from another branch, another history, another version of reality. You could imagine a cosmic ecology, universes feeding off each other, black holes in one universe nourishing white holes in another, a vast interconnected web of realities sustaining each other in a balance we can barely conceive. It's beautiful and terrifying. The cosmos as an organism, metabolizing possibilities, creating and destroying without purpose or mercy. There's a philosophical dimension here too. White holes challenge our notions of causality and determinism. In a universe with white holes, effects can precede causes, at least from certain reference frames. The material ejected from a white hole has no prior cause within our observable universe. It just appears, emerges, with no history we can trace. This breaks the chain of cause and effect that underpins much of our thinking about how the universe works. We're used to asking, why did that happen? And tracing back through a sequence of events. But if white holes exist, some events have no why, no antecedent cause. They're brute facts, givens, starting points rather than endpoints. This aligns with some interpretations of quantum mechanics, where measurement outcomes are fundamentally random, not determined by prior states. Maybe white holes are the macroscopic, gravitational version of quantum randomness, bringing true novelty into the universe. What does it feel like to contemplate white holes? For me, it's a mixture of awe and frustration. Awe at the sheer intellectual beauty of the idea, at the elegance of the mathematics, at the way Einstein's equations contain these mirror structures. Frustration that we can't test them easily, that we might never know for sure, that the universe guards its deepest secrets so jealously. But there's also a kind of joy in the uncertainty, in the fact that there are still profound mysteries left to solve. We haven't figured everything out. The cosmos still surprises us, still offers puzzles that generations of scientists will work on. White holes are a gift in that sense, a reminder of how much we don't know. Let me bring this back to something concrete. What should you, as someone listening to this, take away from the story of white holes? First, understand that the universe is far stranger than common sense suggests. The realm of the very massive, the very fast, the very small, operates by rules that seem absurd when viewed from our everyday perspective. Black holes alone prove this, and white holes, real or not, drive the point home. Second, recognize that mathematics is a powerful tool for exploring reality, but it's not infallible. Just because we can write down an equation doesn't mean nature implements it. The relationship between math and physics is subtle, mysterious, and still not fully understood. Third, embrace uncertainty. We don't know if white holes exist. We might never know. And that's okay. Science isn't about having all the answers. It's about asking better questions, building better tools, and pushing the boundaries of the knowable a little further. There's a beauty in the search itself, in the process of inquiry, that's independent of the outcome. Whether white holes turn out to be real or imaginary, the journey of exploring them has taught us about general relativity, thermodynamics, quantum mechanics, and cosmology. It's forced us to think carefully about time, causality, and the arrow of entropy. It's inspired new mathematical techniques and observational strategies. And it's reminded us that the universe doesn't conform to our preferences, that nature is under no obligation to be simple or intuitive. These lessons have value regardless of whether we ever photograph a white hole. As we approach the end of this exploration, I want to paint one final picture for you. Imagine the universe not as a static stage where events play out, but as a dynamic, evolving structure, constantly creating and destroying, folding and unfolding through dimensions we can barely visualize. In this universe, black holes are sinks, drains where matter and energy vanish from our view. White holes, if they exist, are sources, origins, places where the fabric of space-time wells up and spills over into observable reality. Together, They might form a circulatory system, a cosmic metabolism. Matter falls into black holes, travels through hidden channels, wormholes or quantum transitions, and erupts from white holes, possibly in other regions of space or other epochs of time. The universe recycles itself, not through thermodynamic equilibration alone, but through these geometric conduits, these shortcuts through the structure of reality. If this is true, then every black hole is a gateway and every white hole is a birth. The matter in your body, the atoms that make up your cells, might have passed through countless cycles, falling into black holes, emerging from white holes, scattered and recombined over cosmic timescales. You are, quite literally, made of stardust, but perhaps you're also made of black hole and white hole process material, matter that has journeyed through the most extreme environments the universe can create. That's a profound connection to the cosmos, a lineage that traces back not just to the Big Bang, but potentially through cycles of collapse and rebirth that span realities. Or maybe white holes don't exist. Maybe the mathematics misled us, and the universe is simpler than the equations suggest. Maybe black holes stand alone, maybe the Big Bang was something else entirely, and maybe the mysteries we thought white holes could solve have different answers. That's fine too. Science is a self-correcting process. We propose ideas, test them, and discard them when they fail. The graveyard of physics is littered with beautiful theories that didn't survive contact with reality. Epicycles, phlogiston, the luminiferous ether, steady-state cosmology, all elegant, all wrong. White holes might join them, a footnote in the history of ideas that seemed promising but turned out to be mirages. And if that happens, we'll have learned something valuable. That not every solution to an equation corresponds to a physical object, that the universe is selective in what it actualizes from the space of mathematical possibilities. But I suspect, and this is pure personal speculation, that white holes exist in some form, somewhere, somewhen. The symmetry is too perfect, the mathematics too compelling, the connections to other deep problems in physics too numerous for them to be entirely fictitious. Perhaps not as eternal, stable objects we can observe with telescopes, but as transient phenomena in the early universe, or as the interiors of cosmological horizons, or as quantum transitions that happen fleetingly in the cores of black holes. Perhaps they're real but inaccessible, hidden behind event horizons or cosmological horizons, their effects diluted and scrambled by distance and time until we can't distinguish them from other sources. Perhaps we've already seen them and didn't recognize them because we don't know what we're looking for. This is the state of the field as it stands now. White holes are mathematically predicted, observationally unconfirmed, theoretically controversial, and deeply fascinating. They challenge us to think about time, space, gravity, and causality in new ways. They connect to profound questions about the origin of the universe, the fate of information, the structure of space-time, and the ultimate laws that govern reality. They are a perfect example of how theoretical physics operates at the frontier, proposing entities and structures based on mathematical consistency and seeing whether nature agrees. And so I leave you with these questions to ponder in the quiet moments of your life. What does it mean for something to be real? Is mathematical existence enough, or does reality require observability? If white holes exist but we can never interact with them, do they matter? What would change in your understanding of the universe if tomorrow we confirmed that white holes are real, that the Big Bang was a white hole, that every black hole creates a new universe? How would that shift your perspective on your place in the cosmos, on the nature of time and causality, on the ultimate fate of all matter and energy? These aren't just abstract questions for physicists in universities. They're questions about the nature of existence, about what is and what can be, about the limits and possibilities of reality itself. The story of white holes is unfinished. The final chapter hasn't been written because we don't yet have the observations or the complete theory to write it. Maybe you, or someone you inspire, will be part of the generation that settles the question. Maybe decades from now, a telescope will capture an image that can only be explained as a white hole, and everything we've discussed will shift from speculation to confirmed fact. Or maybe we'll prove they're impossible, and this entire exploration will become a historical curiosity, a reminder of the roads not taken in the development of physics. Either way, the journey matters. As you go about your life, as you look up at the night sky or contemplate the equations that describe our universe, remember that reality is far larger, far stranger, and far more wonderful than our immediate senses reveal. Black holes taught us that the universe contains objects so extreme that space and time themselves break down. White holes, real or imaginary, teach us that the cosmos might be even more baroque, that the laws of physics might allow for structures that defy our intuitions about how things should work. They remind us that we live in a universe of mystery and wonder, a cosmos that rewards curiosity with deeper questions, that offers beauty to those willing to seek it in mathematics and observation. The impossible might not be impossible after all. The reverse of black holes, those cosmic fountains spewing matter and light from event horizons we can never cross, might be more than mathematical phantoms. They might be hiding in the data we've already collected, waiting for the right analysis. They might be transient flickers in the quantum foam of space-time, too brief to observe directly but present nonetheless. They might be the seeds of universes, the wombs from which realities are born, the other side of every black hole in our cosmos. Or they might be nothing at all, beautiful ideas that nature chose not to implement. Either way, we asked the question. We followed the mathematics wherever it led. We confronted the implications, the paradoxes, the wonders, and the terrors. We imagined what could be, we tested what we could, and we remained humble about what we couldn't. That's the essence of science, the heart of the human quest to understand the universe. White holes are a chapter in that quest, a testament to our capacity for abstract thought, our courage to propose the seemingly impossible, and our commitment to letting evidence, not desire, determine what we believe. The universe is vast beyond comprehension, ancient beyond measure, strange beyond imagination. We are brief, tiny creatures on a small planet, yet we can contemplate infinity, probe the beginning of time, and imagine the structure of space-time itself. We can ask whether white holes exist and pursue answers with experiments and observations. That's extraordinary. That's precious. And whether white holes turn out to be real or not, the fact that we can ask the question, that we can explore the mathematics and search the skies, is a testament to the power and beauty of consciousness in a cosmos that seems so indifferent to our existence.
So look up, wonder, question.
Imagine a universe where black holes have mirrors, where matter erupts as violently as it collapses, where the Big Bang was a white hole and we're living inside it still. Imagine the cosmos as a place of perfect symmetry where every entrance has an exit, every sink has a source, every ending has a beginning. And then ask yourself, is that the universe we live in, or is it the universe we wish we lived in? The answer awaits, hidden in the data, encrypted in the mathematics, scattered across the light years. Somewhere out there, reality knows the truth about white holes. Our task, our privilege, our adventure is to discover it.